Sir, move to settings and give the permission for the audio, sir.
Okay, hello.
Sir, this one was coming, sir.
Yes, yes. Now I'm getting the voice now, sir.
Sir, your voice was audible, sir, but the distance was coming, sir.
Okay, so now I can hope so. Now I'm expecting that all our participants, I am audible to you.
Yeah, sir. Yeah, sir.
Yes, that's fine. That's nice.
Yes.
Okay, so I hope so you are not able to start the beginning part because there was voice issue. Okay, so now what is the specification is and what we're going to discuss about this discussion. So, first, here we are going to discuss about the VLSI design. Okay, so in my front slide, the beginning slide which I have shown yet, the what are the VLSI design, what are the VLSI design flow, and what we are going to learn over here. Okay, so shall I repeat from beginning or shall I continue from here? Okay, so now also you are comfortable till here. Anyhow, we have not covered the much content up to here. So now here, what talking about IC. IC, the thing about which are the most comfortably known as the chips in the market. The IC are the integrated circuits. Now there are two types of IC broadly we have. One is the ASIC, which is known as application specific IC, and second one is FPGA, field programmable gate array. So ASICs, okay, from beginning, okay, very good, Tejas. Okay. So VLSI, what the VLSI is, that they are given the name very large scale integration. So VLSI is one of the need of the time where we are going to learn or our student must be knowing about how to design the chips. Okay, so as the process, the VLSI is one of the art of designing the chips or integrated circuit. So here we are going to here we our focus of learning is how to make the IC. Now to designing the IC, what we need? Practically we need transistors. Transistor is a word which is made up of transfer plus resistor. Okay, so transistors are the basic building block for the all the ICs. So either we want to go for a resistor, capacitor, diodes, MOSFETs, power amplifier. These are the certain name of the electronic circuits. Okay, so now how to design the all component? Practically all component is made up of transistors. Like in your college life, you must have known about there are two type of transistor. One is your bipolar transistor, which is known as NPN, PNP, and second one is a MOSFET transistor, which is broadly known as the NMOS, PMOS. Now, how to put? Now we are going to combine those transistors in a such a way that, or arrange this transistor such a way that it can work like a component. I can show you in the later future classes. Like we can add six transistors together to make one logic gates, or we can put hundred or thousands of transistors to make a single circuit. Similarly, the process of integrating billions of transistors into the semiconductor chip to create a complex IC. So practically the number we have got here billions of transistors. Now, to when we're discussing about billions of transistors, it cannot be human oriented task. If you remember your practical lives in your college lab, if you're working with breadboard or PCB, we have some limitation. Like after 20 or 25 component, it is difficult to design that circuit. We cannot go beyond that. Now think about how can we make billions or millions of transistors into this one component, smaller area. Now, okay, that is the art of combining those transistors is called VLSI. Now, there are certain evolution of the VLSI which I'm showing the which derive from number of active devices, basically number of transistors. We say if less than 100, then small scale integration, medium scale integration, large scale, and most standard way of talking about the VLSI is around 1 lakh active component. Okay, so 1 lakh active component in the one IC that is going to define classification of the VLSI. After that, we have the further scaling, further classification, ultra large scale integration. We have the 1 million transistors. After that, again, we have one more category that is called 3D IC. So where we are going to put more amount of more transistor can be put surrounding to the transistor, surrounding to the one vertical chambers. Okay. So similarly here, how to put transistors. Practically, we're talking about how to integrate transistor in a smaller area. We want okay, what we expecting from any IC or any component that is any system is we should have PPA. There are three parameters to be controlled. One is your power, performance, and area. So expectation from our electronic any electronic system, what do we expect? Power consumption should be lesser. Okay, now we want performance. Performance, that is your delay, propagation delay. We want device should be faster. Area is total space taken by the component. We want area should be also less. So we want power should be less, area should be less, and we want delay should be also less. Apart from that, we do have certain secondary parameter also, but practically we are categorizing into PPA, three figure. Nowadays, you can correlate with your mobile phone battery. So, right, previously we have the 100 mAh battery, 1000 mAh. Now we are talking about 6000 mAh of battery. Okay, so which will consume less power because in the battery operated electronic system we have the power is constrained. Okay. Similarly, when talking about delay, so there are certain propagation delay. Some there are some electronic system where propagation delay is the major constraint. Particularly your medical equipment, ECG machine, dialysis machine, where propagation delay are the major constraint. So there we have to focus on the delay. Area, we want area should be lesser because we want our IC should be easy to carry, portable, lesser weight, low space. So we want to be controlled. But practically we cannot control all the three figure: power, delay, and area. If I'm going to do the optimization stand here the how to minimize. If I want to minimize the power, replicator comes here the delay. Power and delay are inversely related. Automatic delay will increase, and there is a another effect will come on the area also. So in the VLSI, there is a one word is called always trade off. Okay, trade off. So we have to minimize one parameter, and for that we need to sacrifice other parameter. Now how much sacrifice we can do, that is your called trade off. Okay, so that is the beginning point of VLSI. Okay, so VLSI trade off say minimize one figure and sacrifice other figure, but how much we can sacrifice that depends on the consumer. Okay, how much it depends on the consumer. Like I give an example of your medical equipment, ECG machine. I cannot sacrifice the delay. Delay is a constraint, but for that I need uninterrupted power supply, so it will consume high power. But for our mobile phone or DC or electronic equipment, power is constraint, so we can sacrifice the delay. Let's go for more friendly. If I take your mobile phone mobile app, if I press touch our mobile app on the screen, it will take some second to open the mobile app. Okay, so we can correlate or we can tolerate this much of delay, but for mobile phone, power is constrained. Fine. So it gives the depending on application. So which type, which parameter to be sacrificed and which parameter to be in constraint. Okay. So we have to focus on or we need to learn how to integrate all the component, all the figure, and finally we can have one complete IC. Okay, so IC is a circuit or a equipment or one IC which can capable to perform a task. Okay, if you I hope so you people have worked with Arduino or Proteus, so you can must correlate about it. Can I have some response from audience? Have you people worked with Arduino or Keel Compiler or Proteus, this type of softwares? Yes, very good, Tejas. Okay, so now what is the situation we have? So first of all, in the Arduino, we are writing the program, we are generating hex file, downloading into the IC. In the IC, we have the memory, flash memory, which is the fastest type of memory nowadays. So in the flash memory, we are downloading the program with the help of PROM so that it can work according to my instruction. Now think about the IC. There are two type of broadly IC we have. One is your ASIC, second one is FPGA. ASIC stand for application specific integrated circuit. Okay, ASIC means there is a one IC which can design only for a one task, only one operation it can perform. But for which purpose it has been designed? Let's take the IC of your NAND gate. IC number is 7400, more popular. So IC number 7400, which designed only for NAND gate, it always remain NAND gate. It cannot change their figure. From the designing to the complete lifetime, it remains a single NAND gate. Those type of IC known as ASIC, application specific IC. Now FPGA are known as the field programmable gate array, which are one of the basic figure is called reprogrammable or reconfigurable. So reprogrammable or reconfigurable means like we have the one board, pre-assembled board in which we can download the program, and this flash memory are erasable. So next day again write the new program. The FPGA board will work like another system. Okay, so there are two type of IC. One is your called static IC, that is ASIC, which is the high performance, low power, and it is the fixed functionality, only one task capable to do. This is all the generally all the commercial IC are ASIC. Okay, all the commercial IC are the ASIC. Your mobile phone, your microwave oven, in the televisions, everywhere, whatever IC you are watching for commercial, that is your ASIC. FPGA generally used for the research and prototyping. Okay, FPGA, where we are going to discuss about some programming language that is known as HDL, hardware description language. From there, we need to generate bit file, that called bit stream file. Those file we need to download on the FPGA memory, similar to Arduino, and it can work according to instruction. After 1 hour, download the new program. It will work as a new system. Okay, so FPGA are used for the prototyping purpose, not for the commercialization. So you given the difference that FPGA is faster in time. So what we have to do, only we write the program, generate bit file, it can work. But in the ASIC, we have to do lots of difficult tasks. Here we need design team and we need fabrication team. So today I will talk about this word fabrication and chip tape out. Okay, let's continue with the next topic. Okay, now as I told you, we have the two type of transistors. Uh, Basically, transistor are the basic block. Practically, logic gate is considered as the design basic block for the designing of the circuit, but logic gate is also made up of transistors. So we have the bipolar transistor or we have the MOS transistor. So we know as well bipolar transistor which okay bipolar transistor which are known as fastest type of transistor. But most transistors are known for the low power consuming transistor. Okay, that is the major interest. So bipolar is known for, like if you remember, there are eight IC logic. We have the fastest type of logic is ECL, which is made up of bipolar transistor. Low power consumption are MOSFET, CMOS logic, that is the MOS transistor. So now when we want to have the faster transistor or when we want to use smaller low power consuming transistor, that depends on the consumer application. Apart from it, I have given some major area, other type of figure, like mostly we have the power consumption, we can have the reliability. Now reliability is a one figure which gives us the whether the our device can operate reliably under harsh condition or constrained condition. Like we know in the commercial IC, the range of temperature is minus 25 to 120 degrees Celsius. Or sorry, 60 to 20 degrees Celsius. Like temperature zone are different. The whether my device can operate satisfactory in every temperature, or when we want to go for power consumption under the noisy environment. If my device are passing through nearby transformer, what are the effects? So we have to discuss about reliability of the device, whether my device is reliable and scalable. Scalable going to discuss that how can we make here the larger scale or can we go for the more number of device can be translated from the single design. Okay, so for that we have the one interesting word that is called lithography. There is a one word called lithography. So that is going to derive from the scalability. Okay, so practically we are saying about this word transistor. Sometimes we have to go for ECL logic, that's the fastest type. Somewhere we have to go for CMOS logic, that is the low power consumption. Okay, so this is one of the application which I have shown here that transistor. Okay, one of the very basic application for electronics are the transistor can act as switch. I hope so all are agree with this. Transistor can act as a switch, basic application. Or you must be knowing about transistor operate in a transistor can operate in three different operating region. One is the cutoff, linear, and saturation. So here cutoff mode and saturation mode. Those are the two constant mode that can be used for making the transistor in on state and off state. Cutoff mode where the transistor work on the off state and saturation mode where the transistor can work on the on state. So this is the diagram which I am showing that when we want to apply a switch, the switch can be act as the transistors. So in a transistor, we have the terminal source, drain or gate or base control emitter. So from the central zone or central terminal, if I apply some input, it will connect the both terminal and allow to pass a current. As a result of that, we understand that a transistor can act as switch. So similarly, we can have other application like mostly using amplifiers, oscillators. Now, how many transistor we can put? Those are the coming as part of our design. Okay. So you are up to comfortable. Everyone up to here comfortable? Okay. Okay. For now, from this slide onwards, what I'm going to discuss about the for any design. Okay. Generally, a designer have got when designer are getting certain tasks from market or certain vendor like requirement of IC to for any application. Okay, so first of all, what a designer need to do, they need to do a spec. First topic is the specification, what they have to design. Now, what on the first of all we have to do some manual work or designer are doing some manual work, so they are doing some paperwork designing. After that, implement. Now, implementation is a topic where we are going to discuss about we have to make the circuit designing with the help of logic gate or with the help of transistors. Now, third steps come here that validation. Validation comes here that whether the circuit which has been implemented is it correct or not. For the validation which give one of the result, one verification, yes, it is the validated. When our design is completely validated, then we have to go for the market. Okay. Now this is one of the very primarily and very small design flow which I'm going to discuss. So that for any design, the first of all we have to go for requirement study. Requirement study like we can go for by means of survey or by means of previous session, previous experience or with the help of some customer requirement, which type of IC they want. Now, based on their requirement, we have to derive the spec. Specs comes here that like in our IC, how many inputs, how many outputs, what should be the range of power consumption, what should be the range of area, some mm square or micro mm square. Similarly, what is the delay, how much delay or expectation. Now, if they're working for RF work like microwave or antenna, so what are their specific limitations like SNR or decibel gain, noise margins? So we have to think about all type of electronic spec of that. Now, by considering those spec, try to implement on transistor level circuit. But for designing this transistor level circuit is not the manual task. We need to take the help of software. Those software are known as EDA, Electronic Design Automation. Okay, take this word naturally. Electronic Design Automation. Now, with the help of the software, we will able to generate the circuit. Now, validate. Validation, you must be knowing about one word called simulation. Okay. Simulation, where we are going to simulate the circuit and based on the circuit connection, it will generate certain output. That is your call. Yes, our design is validated. Now, after validation, what we have to do? We have to generate one hex file. But in this electronic circuit, we are knowing the one word called GDS. Okay, that I'm going to discuss here that for any VLSI design, we have that broadly classified into the two categories. One is your front end, second one is your back end. Front end, that is my spec. After the system spec has been confined, then we have to talk about the architecture, block diagram, function block level of architecture, where we are talking about block diagram. We can make block diagram of different component and how they are connected with the help of wire. On the paper, we can make this type of architecture. It is called functional architecture. After that, we can go for functional verification. Functional verification is a part of simulation. During this functional verification, we need one test bench file. So that we're going to discuss about test bench file very soon. So we will write one test bench program. We can go for functionality verification. Once my functionality, if there are certain error arises in the simulated waveform, we have to recorrect our program or we can go for next logic. That is called logic design. Logic design where our program, because I told you we have the billions of transistor, billion logic gate, we cannot do the manual task, we can go for programming wise. The programming wise, for every program, we are going to convert into gate level representation. That I'm going to discuss about logic design. This conversion is called synthesis. Okay, that is what I've written here, the synthesis phase. It is a process of translating a Verilog code or Verilog program into the gate level netlist representation. Okay, that is called logic design. After that, again, we can go for a logic verification. If the mic completely verified, then we can go for the circuit verification or circuit design. Okay, the circuit design where Okay, the circuit design here we can have the circuit representation, then again circuit verification with the help of test bench, and finally we can have the very interesting word that is called physical design. Remember the physical design is one of the very nice skill of the VLSI industry, in which we are targeting our all the circuit at transistor level, which is mostly known as the layout representation. Okay. The layout representation, we will talk about resistance, capacitance, inductance, okay, parasitics. These are the certain technical words arises. Again, we have to go for again physical verification, that is the help of simulation process. So here I have this complete one of the design flow which I have integrated both front-end design, back-end design. The front-end design broadly classified when talking about programming side, Verilog code, block diagram, digital logic. But when talking about the word physical implementation, physical design, that is your layout. Okay, and so in that case, that is known as your layout phase or backend design. Okay, how so now you got some idea how to start with that, how to go for spec. First of all, spec. It is similar to the work you people must have done in your lab. Whenever you have got some practical experiment. So first of all, in the paper, we are drawing some circuit diagram. Then we are mapping on the breadboard. Now we are applying the input from our trainer kits and we are generating the output on LED. We can correlate the same thing. First of all, we have the one architecture diagram which you have to redesign block diagram. Verification is the apply the input and you will get some output. But here it is a software that is called simulation or verification. Now here this is called extension, the synthesis, layout, circuit verification. These are the extension or a new update for the electronics engineer only. So they only know about how to map a design into the physical implementation view. Okay. Okay, now think about more detailed diagram. Here we are talking about the word complete. One word is called ASIC flow, design flow, or GDS flow, RTL to GDS. Okay, so here, if we're talking about the first on the same way, we have the aspects, specification, architectural design. So architectural design, here I have classified that is my block diagram. Here we have to define all the specs, functionality, PPA, input, output ports, everything to be defined. Afterwards, the next very important steps come here, the RTL coding. Here RTL stands for resistor transfer level. Okay, resistor transfer level, which is the RTL coding that is snips. For that, we need one word called HDL, hardware description language. Okay, hardware description language. There are two types of HDL. We will come to know that one is your VHDL and second one is Verilog. Okay, there are two type of HDL. We will come. The snip of the program which I have shown over here, that is your Verilog language. Majorly, the more I think more than 75% of the industry are focused on Verilog language. Okay, there is another language. We have the VHDL, which is no doubt they have their own importance, but their usage are very lesser. Okay. So VH Verilog, that is the industry-driven language, and second one is VHDL, which stand for very high speed integrated circuit. Okay, this is the one in the VHDL. It is stand for here VH. There's a one is there's some word are silent actually. VHSIC. Okay. Very high speed integrated circuit. After that, HDL, hardware description language. Okay. Okay, there are two type of language for designing part. That is your Verilog and second one is VHDL. So from this designing part, we can generate the programming file of the designer, programming file of the any specs. Okay, so after that we need for functionality verification, that is your simulation or verification task, right, with the help of test bench. Second step comes here synthesis. Synthesis, I told you, it is a RTL, it is a process of converting a program into connection wise, logic gate wise orientation. Like whatever the program we have wrote, for every program it map into the netlisted diagram. But to map into netlisted diagram, the software going to take the help of one library. Okay, they are going to take one help of library which is known as PDK, where PDK stand for Process Design Kit. Okay. Process Design Kit. So every software have their own IP. Where IP in my means IP is intellectual property. So they have the PDK file. So for every program, they will look into the library and they will going to map or going call one component and do the connection according to requirements. Now PDK is the technological library which going to classify some technology of the circuit or technology of the transistors like 180 nanometer, 90, 360, 45 or 10 nanometer or 32 nanometer. So which what is the size of technology we have designed, that is the going to map on this logic synthesis. Okay, after the synthesis again we have to go for verification. Again do the one verification of this circuit whether my design is correct or not. It means apply the input, again check the output. Are you getting the correct output everywhere? Once your synthesis is over, then we can have physical design. That is a very interesting skill of the industry, PD flow. It's mostly known as the word called physical design. The physical design, so the diagram which I have shown, here it is going to discuss for every synthesized circuit. Here we have a layout map, that is one called layout. Layout, or we can go for connections, transistor driven diagrams. Here we will discuss about RLC, parasitics, all the analog electronics or analog figure to be discussed during this simulation. Finally, we can go for again one physical sign off. Here we will discuss one topic called timing analysis to be discussed, STA part, and fabrication. Now from here these are the my fabrication steps. Now these three steps, fabrication, packaging and chip layout, those are not given by the designer. Okay, up to here this is a task of the designer team. If I'm going to discuss about life cycle of the complete VLSI chip, we have the two different teams. One is a designing team, second one is your fabrication team. The role of designing team is to, with the help of this spec, try to do the physical design, physical significance, and generate one programming file. Those files are known as GDS. Okay, GDS file, graphic database system or graphic data system. So GDS file, this file is similar to the hex file of Arduino. Now this file is ready. After that, we have to send the file into the process team, fabrication team. They are sitting to the some other country. Okay, they do not know about the what is the spec, what is the RTL code. They're not interested into that. They will only look into the GDS file. From the GDS file, they will go for the chip fabrication. Okay, so first of all, they will take silicon wafer. In the silicon wafer, we have to do around more than 30 or 36 steps. We have the more repetitive steps like oxidation, lithography, etching. Lots of physical and chemical steps are there. After that, the information given by this GDS file, they will map into the IC, and finally they will cut the IC into the packaging form, and we will get one chip into the market. Okay, so now here, as we told you, there are two teams. One designing team, the how efficient this GDS file has been designed by the IC flow designers. the IC will be more performance. IC performance will be better because this team do not have idea about the design process. This team must be knowing only GDS file. And I will show you the snip of GDS file. Here we have only information in the symbol format or binary format. Okay. So now the designer team which are playing with simulation. So before sending the GDS file into the market, we must have to do rigorous simulation more than 1,000 times, 10,000 times. Do the rigorous simulation so that all the corner, all the error, everything has been validated. Okay. Because we know up to designer team, up to here we have the task on the software. But after that, if I send this information to the fabrication team, they will fabricate the IC and IC will come to the market. Now in the market, if there are certain faults, some error or arises, it is a heavy loss for industry. If there are certain IC has been got some error or not working, performance are not as specs, then there will be some heavy loss for industry. So industry do not go for that type of losses. So they want all the IC must be every specs must be validated for every corners, every aspect during the simulation world only. Okay, and in the if talking about the VLSI industry, there are lots of job opening coming for the designer team. Around 70 to 80% jobs are in the designing part. Only the we have got more expertise on the hardware or fabrication. They have to go for less number job opening into the fabrication team. Okay, because here a small error can go for the completely failure of the IC. Fine. So also getting what is one question here was what is simulation? Like simulation is a process of functionality verification. Like we want to verify whether the my IC is correctly working or not. So what you're doing in the lab, we have the one called IC tester. We putting the IC into the tester, apply the input, and check the output. Whether my every input output is working or not. That is called simulation. Okay. So simulation is process of verification. But for the in the software, we will write we have the software base that is called test bench based simulation, not the manual switch input or output simulation. Okay. Okay, back to here. Now there are two type of world we are talking about. One is your digital flow that I discussed about this word that is called digital design. We have the two type of designing we have. One is your digital design, one is the analog design. Okay. The digital design, when we're talking about the information in the binary world, that is 0 and 1, that is your digital design. But we're talking about analog in the nature, that is your analog design flow. Currently the slide we have discussed here, those are the digital design flow. The next design which I'm talking about right now, that is the analog design flow. Now you can have your own classification. Digital component, digital lab, and we have analog lab. The digital, you are working with logic gates, decoders, multiplexers, flip-flops. In the analog lab, we are working with diodes, transistors, schematic trigger, working with amplifiers, okay, regulators, comparators. So we are with op-amps. These are the certain IC which are categorized for analog IC. Some IC are the digital IC. Now for design filters, very good Tejas. So if we're talking about analog design flow, how to make the analog component. So for that we have the separate flow, design flow and separate software. Okay, in our session, I will discuss both type of simulation world, digital simulation world as well as analog. So analog simulation world start with the same design specs. Now here the one topic come here the schematic design. Like in the digital design, what we're talking about RTL coding. programming with Verilog. Now here the same steps here, the designing of circuit at transistor level, that is the transistor is called the word schematic. Okay, schematic design. Then we can go for the again simulation. Okay, the simulation what is called pre-layout simulation. Layout comes here the physical design. Okay, so before layout, we're going for pre-layout simulation. And then again, one question mark, whether my specs, what we have started with specs, that the specs met. If no, again change the program, not the program, change the schematic. Schematic, I think about one arrangement of transistors. Like we can put 10 or 12 transistor in a series or parallel or some connection so that we can able to design some circuit. After the specs are satisfied, yes, we satisfied my specs are met. The next topic comes here layout. Okay, layout design. Layout is your where we are talking about the world physical world. Physical world comes here like silicon. We discussed about metals. Then we will go for the annual. Then we can go for the holes and complete connections, wires. So we will discuss about what are the physical component required to design the some circuit. Okay, this word is called your layout designs. Okay, so as we know, our silicon, all the circuits are made up of silicon. Silicon is semiconductor. Now, how much silicon require to design one circuit? That's going to devise the cost of IC. If I put more amount of metal, the resistance will high because we know R equal to rho L by A. If I put transistor, if I put component at larger space, we will get high capacitance because we know C equal to epsilon A upon D. So we have the think about RLC. We're going to about physical world actually. Now, when we have joined this physical world, we have to check whether the my design is correct or not. So for that, there's a two rules are there. One is the that is called DRC and LVS. DRC stand for here design rule check. Actually, in the very old technology, in the I think in 1970s, mid Conway, there are two scientists. They have proposed certain rule for regulating the layout of the circuits. That the rule are given as DRC. Still, we are following the same rule of the mid Conway. And DRC, there are around nowadays rules has been increased. They are adding the more rules. Now it can around 200 or 300 rules are there. So we don't have to sir in the digital design. Of course, Abhishek, we have the flip flops. We will take this type of programming very soon. Okay, so we're talking about DRC LVS. So DRC stand for here design rule check. LVS stand for layout versus schematic. So whatever the DRC stand for, yes, layout versus schematic. So DRC is the like rules, bundle of the rules which will go for distancing. Distance between two component, area between two component is satisfactory or not. That is your DRC. Now LVS comes here that how the schematic has been designed, whether the layout is same or not. If they both are same, that's good. If no, then we have to do the redrawing or reconstruction of the circuit. Now there are some there is a one factor is called parasitics. Very dangerous word for the VLSI people are the parasitics, which is mostly made up of resistance and capacitance RC. Okay. Uh, yes, parasitics. So parasitics are the unwanted capacitance. Like in the electronics, you must be knowing about mutual. One word is called mutual inductance, mutual capacitance, crosstalks. This type of words will come. So whenever two parallel lines are close to each other, there will be unwanted capacitance will added. Those are the parasitics. Now think about your PCB. In the PCB backside, if lots of copper wires are running across horizontal or vertical, crossing to each other, and we know that there is a suppression of air gap. Because of that, we have the epsilon value. So it must be some capacitance. So how much unwanted capacitance our circuit can withstand? So that we are going to calculate into parasitics. Okay. Afterwards, again, there's a one. Again, we have to go for simulation. They call a post layout simulation. So whether our design able to work with parasitics or not. If yes, then we can go for GDS2 file. The GDS file which we have the same name, graphic data system second. There is second version. If no, again go for the symbol creation. Okay, the circuit steps are only 72 steps that you're watching. But when you're going to design this type of circuit, it will take some learning or some it will take some constraint or some learning how to design the circuit in the given constraint. DRC, LVS, simulations. Fine. So these are certain words which are regularly used into the VLSI. Okay, that was the digital flow. Here we have the analog flow. Okay, up to here comfortable or certain inquiry up to here? Fine. Okay, so now here up to here we have given the one list flow. So but we know there are millions or billions of transistors are arranged. So we need some dedicated software. So which type of software we are going to use? Okay, so we must have to go for software. I think there are some images. I will skip this slide because it is blurred. Okay, so there are certain software we need to use. Okay, so those software are given by a certain designer or not designer. We have the certain vendors. So practically in the VLSI market, there are three major vendors we have. One is the Cadence, Synopsys, and Mentor Graphics. Nowadays, Mentor Graphics has been purchased by the Siemens. So basically, we have the Cadence, Synopsys, and Siemens. Okay, so Cadence are the providing some software which are the known as the Cadence for digital flow and which for the analog flow. Okay, so Cadence and Synopsys are the two major vendors which are providing the software for the designing part, and Siemens are providing very nice software that is called Caliber or IC2, which are mostly have the major high quality for the verification, physical level verification. Okay, so now here all the steps are must be went through certain software which are known as EDA tool. Okay, EDA softwares. So this is one of the slides which this is one of the slide which I have shown the complete layout. One of the layout designed by our team of ALU. The circuit given the test PNR given by the ALU layout. So it is very difficult to think about how to make these types of connections. Somewhere we have the red color, green color, or pink colors. So these color are going to give us the certain understanding which type of wirings we have performed. Okay, the snips which I have shown, which I have designed with the Virtuoso. The Virtuoso is one of the software given by Cadence. Okay, Cadence is one industry we design this Virtuoso software, and they are providing some bundle of software for front end, some bundle of software for back end. Okay, so wait, here I think here I'm going to discuss about what are different software going to learn software we have. Okay, so first of all, as I told you, here we have the Cadence software. The Cadence going to basically we are using here that is one your Cadence is providing the Virtuoso that is for analog component, and let me write this part. Okay. So if you have access about this software, then you must practice with that, because in the industry also we have the similar type of exposure. Cadence providing the virtuoso and they providing the spectre, that is simulation, and providing the asura for the designing the layout. Similarly, in the digital world, they provided the NC SIM, Cadence NC SIM, they provide the Genus, and they provide finally Innovus for the physical design. Okay, so we have a series of the software to starting from spec, simulation, synthesis, implement, and finally implement GDS file. Okay. Okay, but back to here. So here in this diagram which I have shown, so somebody can comment like which type of diagram I have shown over here. If you have learned about it earlier, which type of diagram it is? Schematic. Okay. So what is which type of? If I give you a hint, which type of logic gate it is? Inverter. Very good. So this is the inverter. Inverter is mostly known as the NOT gate. So the NOT gate, which is upper part, which I have shown you, the made up of P-type MOS and N-type MOS are in series. So it is known as the NOT gate or one inverter. Second diagram, which I have shown here for layout. Okay, this is a layout where every symbol has been replaced or substituted by the physical component, and they have their own color coding. Like here we have VDD, ground, red color represent for input. The red color represent here silicon, which is known as the polysilicon. Green color here, this color represent the p-type MOSFET. Green is output, no, output taken from the center part as a blue color. Practically this color is used for the pink color or orange color, PMOS. NMOS is used for the green. So whenever this red line crosses the green line, that make here one N-type MOSFET. Whenever this red line crosses this pink or orange color, that going to make here P-type MOSFET. And whenever these are the known as the layers, one layer crosses to other layer, we need to provide some connection, which I have shown by black color. Those are the connections. Okay. The third diagram which I have shown you here, that is the GDS file of the inverter. Okay, now think about the situation. The designer team, they have do the schematic, they have done the layout. After that, they have went for this GDS. This GDS file has been sent to fabrication team. They will do the physical and chemical process from the silicon to silicon wafer. They will fabricate the chips. Now they do not the designer, the fabrication team, they only know what is the meaning of one, what is meaning of zero, what is dot, what is the y 3 2. They know only this symbol. Okay, so the role of software is to generate this schematic to layout to GDS. Okay, so designer team, which we are going to, our sessions, which will comprise this type of conversions, and we will play with the EDA tool. Okay, these are the certain well-known EDA tool. Apart from it, which I have showcased over here, that is your Cadence and Synopsys, Siemens are the very popular. Apart from that, we have the certain tool like the Keysights. We can go for Agentics, we have Juken, edX, and we have the one very nice software that is called your AMD. Okay, AMD is one of the very nice industry, and the 3 year back they have purchased one software provider. It is called Xilinx. Okay, Xilinx is one of the very nice software provider which provide EDA tool for FPGA. Okay, FPGA based programming. So FPGA we have discussed in the front in the beginning, ASIC and FPGA. So all the till now digital flow, analog flow, they can go for the either EDA flow, anyone, it EDA flow. But AMD, they have taken the Xilinx. Xilinx is mostly preferred for the front end. Like we were discussed about the Verilog programming, simulation, synthesis. But after that, we have to go for FPGA based implementation. Now, in the FPGA based implementation means we will take the first a family of FPGA like Vertex or Spartan, Nexus, different type of FPGA family. Now, for which family we want to generate one file that is called dot bit file, bit stream file. Those bit file we have to download into the flash memory of the processor, and it can work according to our written code, similar to Arduino. Okay, so these are the certain well-known EDA tools. That some tools are the general purpose. Some of the tool mostly used for the some specific. Like ANSYS, they are mostly used for MEMS. Keysights, they are mostly used for the providing a specific memory related task or antenna related designing. Okay, so there apart from it, we have the lots of other software also which can use only for some specific situation. Okay, like here these are the certain major tool, but we know tool or maximum tool are the licensed one. We cannot for the very high cost EDA tool like Synopsys, which provide the IC2, Prime Time, VCS. Cadence provide the Virtuoso, Innovus, Exilium, and Siemens provide the mental graphics type of software. Okay, we have some software which is related to nowadays open source. If you think about this Open Road is a very nice initiative where we can talk about the free. We can go about the free of cost accessing of certain tool for some time. You can go Electric, Alliance, and Glade layout editors. Okay, so these are a certain EDA tool which is mostly three are the majorly ruling of the industry. Apart from it, we have some open source software given by the certain industry or some institution, eSIM. They're given by the IIT Bombay, NGSpice, XM, KiCad, Magic. Magic is mostly used for the layout designing. YOSIS that is used for synthesis of digital designing, OpenLAN. And nowadays we have the one a Sky PDK, divided by 130 nanometer. And here I can mention there is one website if you able to explore that is called Tiny Tape Out. Okay, that is called Tiny Tape Out. You can bookmark this website, and they have the certain funding they have received from the some well-known industry and the research organization to explore or to expand the knowledge of VLSI and support for chip fabrication. So they have collaborated with IEEE, and they are time to time they are organizing certain event where anyone can go for chip fabrication at free of cost. Okay, so what we have to do, we should have access of some software from where we can generate GDS file. Those file we have to ship outside, not in our country, abroad the country. They will fabricate on this 130 PDK, open source Skywater 130 PK BDK, which is developed by Google. Okay, and they can fabricate and they can send back to our fabricated IC. So here one of the new thing you can explore about it, tiny tape out. Fine. So these are the certain things which I have discussed today. What are the design VLSI design flow, and for every design flow, we should have access of certain software. Okay. So this is only thing which I brought for today, and if you have certain query or something to ask, I'm available to you. Okay. So nobody are going to raise a query. I hope so. You have understood something. Uh, Still note will be provided. Yes, I will provide the presentation which I'm going to use. Okay, and time to time in our WhatsApp group, you people must have. I will share some of the small software. So have you people worked with some software called DSCH? Because we will take one very small software DSCH to schematic design, and that software is open source. I will share with you. And secondly, we can use certain some online based compiler, online based simulator where we can go for notes will be provided Tinkercad. Yes, I will Tejas, I will provide the notes. Tinkercad, you have people have worked. Okay, Tinkercad is there only for that. That can be used for the designing of digital world, digital analog world. Okay, similar to Tinkercad, here we have one software called DSCH where we can translate our design into Verilog. And I will use certain online simulators for the Verilog. If you have worked with the EDA playground, that will be very nice. Or we can go for some alternate. Okay, so I hope so this is enough sufficient for today. So today I have just started with our quick first part of the VLSI, and when we meet tomorrow back on the evening, we'll discuss the next topic. That is a circuit designing space. Circuit designing about our circuit. Circuit designing with the help of logic gates or with the help of transistors. Okay, so if no questions, so shall I bind up for today or should I wait for some time? Somebody have certain queries? The notes I will share in my WhatsApp group itself. Okay. So thank you all for this hour and for the presentation. So hope so we will meet tomorrow. We can going to meet by tomorrow again on the same time. Thank you.